Across the entire cosmos, through every star, every planet, every living body, an invisible river is always flowing. It moves without resistance, without weight, without sound. It does not stop for planets, does not slow inside stars, and does not leave a trace as it passes through your bones, your blood, your atoms. These are neutrinos, the most abundant massive particles in the universe, and yet the most easily overlooked. Every second, more than 1 trillion of them pass through your body, and you will never feel a single one. For most of human history, we believed the universe was shaped by what we could see: stars blazing in the darkness, swirling galaxies, clouds of glowing gas. But beneath that visible cosmos lies a fainter, ghost-like world, a realm of particles that rarely interact, rarely reveal themselves, and yet play a crucial role in the story of cosmic evolution. Neutrinos are the silent witnesses of the universe, present at the birth of the cosmos, forged in the hearts of stars, unleashed in the fury of supernovae, and traveling across billions of years without losing a whisper of their energy. They are everywhere and nowhere, always passing through us, but never touching us. In this video, we will explore what neutrinos truly are, how they are born, how they move through matter as if it were transparent, how they shape the formation of galaxies, and how they may hold clues to some of the deepest mysteries in physics, from the origins of matter to the nature of dark matter itself. This is a journey into the ghost universe, the hidden world that exists beside us yet remains forever out of reach, a world made not of light, but of shadows that travel at nearly the speed of the stars themselves. Neutrinos are among the strangest and most elusive particles ever discovered, quiet passengers of the universe that interact so rarely with ordinary matter that they have earned the title ghost particles. At their core, neutrinos are incredibly simple. They carry no electric charge, and their mass is so small that for decades scientists believed it was exactly zero. Today we know neutrinos do have mass, but it is astonishingly tiny, millions of times smaller than the mass of an electron. Their neutrality and near weightlessness give them the ability to slip through matter almost without leaving a trace. There are 3 types, or flavors, of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. Each is associated with its corresponding charged particle, and yet neutrinos can do something no other known fermion can. They can transform from one flavor into another as they travel through space. This behavior, called neutrino oscillation, is one of the strongest clues that neutrinos must have mass, even if that mass is unimaginably small. The secret behind their ghost-like nature lies in the weak nuclear force, one of the 4 fundamental forces of nature. Unlike electromagnetism, which allows charged particles to interact strongly and frequently, the weak force is subtle and rarely acts. It governs processes like radioactive decay and neutrino scattering, interactions that occur with such low probability that a neutrino can pass through light years of solid lead without hitting anything at all. A typical neutrino could pass through the entire Earth as if it were passing through a cloud of smoke. This near invisibility makes neutrinos extraordinarily difficult to detect. They do not interact with electric or magnetic fields, they do not ionize matter, and they rarely collide with nuclei. To capture even a handful of them, physicists must build enormous detectors, tanks of ultra-pure water buried deep underground, or cubic kilometer arrays of sensors frozen under Antarctic ice, all waiting for the faintest blink of Cherenkov light produced when a neutrino finally, and improbably, interacts. Neutrinos are the most abundant massive particles in the universe, streaming through galaxies in unimaginable numbers, created in nuclear reactions inside stars, in supernova explosions, in cosmic ray collisions, and possibly even moments after the Big Bang. Yet despite their abundance, they remain the particles we understand the least, fragile clues to the deep quantum structure of matter, hiding behind a veil of near-perfect silence. To study neutrinos is to study the shadows that matter casts at the smallest scales, the quiet echoes of processes that shape stars, galaxies, and perhaps the structure of the universe itself. Every second of your life, you are crossed by a river of particles you will never feel. Around 100 trillion neutrinos pass through your body each second, silently, effortlessly, without slowing down or interacting in any meaningful way. They stream through your skin, your bones, your atoms, and continue on as if nothing were there at all. To a neutrino, the entire Earth is almost perfectly transparent. This astonishing behavior comes from the way neutrinos interact with the world. They respond only to the weak nuclear force, a force so subtle and so rarely engaged that most neutrinos will never collide with anything, not in a human lifetime, not over the lifetime of the Earth, not even over the lifetime of the universe. A neutrino could pass through a light year of solid lead and still emerge untouched. Matter, from the neutrino's point of view, is mostly empty space. The neutrinos that pass through us come from many sources. The dominant stream originates from the sun's core, where nuclear fusion transforms hydrogen into helium, releasing torrents of electron neutrinos. This solar neutrino wind floods Earth in numbers so enormous that detecting even one interaction requires enormous, sensitive detectors buried deep underground. Another population arrives from cosmic ray collisions in Earth's upper atmosphere, high-energy particles from distant galaxies slamming into atmospheric nuclei and producing showers of neutrinos. Still others come from supernova explosions, events so violent that they release more neutrinos in a single second than the sun will emit in its entire lifetime. And then there is the most ancient stream of all, the cosmic neutrino background, relic neutrinos that have been traveling freely since the universe was 1 second old. These nearly undetectable particles are fossils of the Big Bang, filling space with a whisper of the universe's first heartbeat. To planets and stars, neutrinos behave no differently. They pass straight through gas giants, through stellar cores, through white dwarfs and neutron stars. Even the densest objects in the universe barely slow them down. Neutrinos do not care about matter because they barely see it. Their interaction probability is so small that only a tiny fraction ever collide with anything, and those collisions occur by statistical accident, not intention. The transparency of the Earth, and of stars, planets, and galaxies, to neutrinos reveals a profound truth. The visible world, for all its solidity, is mostly empty. The particles that define the structure of our bodies, the walls of our homes, the crust beneath our feet occupy only a thin fraction of the volume we perceive as solid. Neutrinos simply remind us of this by passing through everything as if the universe were made of shadow. In studying these ghost-like particles, we glimpse a deeper layer of reality, one in which matter is not a barrier but a suggestion, and where the true structure of existence is far more porous than our senses would ever allow us to believe. Detecting a neutrino is like trying to catch a single snowflake in the middle of a hurricane with a needle. These particles interact so rarely that most will pass through the Earth, the detector, and everything inside it without ever leaving a trace. To observe even a handful, scientists must rely on some of the most ambitious and imaginative instruments ever built. Detectors that use mountains, oceans, ice sheets, and underground caverns as part of their design. One of the most remarkable is IceCube, located at the South Pole. It is not a laboratory in the traditional sense, but a 1 kilometer wide cube of Antarctic ice transformed into a cosmic observatory. More than 5,000 optical sensors are buried deep beneath the surface, arranged like strings of glowing beads in the transparent ancient ice. Most neutrinos pass through without interacting, but on rare occasions, a high-energy cosmic neutrino will collide with a nucleus inside the ice. This collision produces a charged particle that moves faster than light travels in ice, not faster than light in vacuum, but fast enough to create a cone of blue Cherenkov radiation, a shockwave of light similar to a sonic boom. When this happens, the sensors awaken, capturing a faint flash that marks the passage of a ghost from the distant universe. On the other side of the world, in the mountains of Japan, the Super Kamiokande detector sits in a cavern a kilometer underground. It is an immense chamber filled with 50,000 tons of ultra-pure water, lined with thousands of photomultiplier tubes that watch the darkness for sudden bursts of blue light. When a neutrino interacts with the water, an event so rare it may occur only once in hours or days, the emitted Cherenkov light forms perfect, expanding rings on the detector walls. The purity of the water and the exquisite sensitivity of the sensors allow physicists to reconstruct the energy and direction of the neutrino that created them. It is like catching a whisper by watching its reflection ripple across a lake. Both detectors rely on the same principle. Because neutrinos interact so rarely, the only way to detect them is to build detectors of enormous volume. A cubic meter of water or ice is effectively silent. 1,000 cubic meters hardly improves the odds. But 1,000,000 cubic meters, a cubic kilometer, becomes a canvas large enough that a few rare interactions will appear. This is why neutrino detectors are among the largest scientific instruments ever built. Their size is not a luxury but a necessity. Neutrino detection is a triumph of patience, scale, and imagination. By waiting in the deepest darkness, under ice, under mountains, under oceans, scientists listen for the faintest signals from particles that almost never speak. And yet, through these fleeting interactions, we learn about exploding stars, collapsing black holes, cosmic rays, the interior of the sun, and the earliest seconds of the universe. Catching the impossible reveals worlds we could never see otherwise. One of the most astonishing discoveries in modern physics is that neutrinos, these silent, ghost-like particles, can change their identity as they travel. An electron neutrino born in the core of the Sun may arrive at Earth as a muon neutrino. A neutrino produced in a cosmic ray collision in the atmosphere may transform into a tau neutrino before reaching a detector underground. No other known particle in the Standard Model behaves this way. Neutrinos drift through the universe like shape-shifting shadows. This phenomenon is called neutrino oscillation, and it shattered one of the long-held assumptions in particle physics, that neutrinos were massless. For decades, the Standard Model treated them as particles with no mass at all, mere wisps of the weak force. But when scientists detected fewer solar neutrinos than predicted, they realized something profound. Neutrinos were disappearing not because they vanished, but because they were changing flavor. And flavor change can only occur if neutrinos have mass. This discovery was so revolutionary that it earned the 2015 Nobel Prize in Physics. The mechanism behind oscillations is subtle and deeply quantum. Each neutrino flavor, electron, muon, tau, is not a particle with a fixed mass. Instead, each flavor is a quantum mixture of 3 different mass states. A neutrino is born in a specific flavor state, but as it travels, those mass states evolve with slightly different speeds because their masses are not identical. Over time, the mass components drift out of phase, recombine, and interfere, causing the neutrino to rotate from one flavor to another. It is as if a single particle carries multiple overlapping identities, and the act of traveling through space changes the balance between them. One moment it behaves like an electron neutrino, the next, like a muon neutrino. The farther and longer it travels, the more pronounced the oscillations become. This discovery forced physicists to rewrite part of the Standard Model. If neutrinos have mass, then mass itself must arise from mechanisms that go beyond the Higgs field alone. Neutrino oscillations hint at new physics, perhaps right-hand neutrinos, perhaps sterile neutrinos, perhaps interactions that lie outside everything we currently understand. They may hold clues to why matter dominates over antimatter in the universe, or why particles have the masses they do. Neutrino oscillations reveal a profound truth. Even the faintest particles can reshape our understanding of reality. These transformations, invisible to our senses, point toward a deeper structure of the universe, one woven not from fixed identities, but from quantum superpositions that evolve with time. In studying neutrinos, we are not just observing particles that change flavor. We are witnessing matter exploring all the possibilities allowed by the quantum rules of existence. When a massive star reaches the end of its life, its final moments unfold in a way that defies ordinary intuition. To an outside observer, a supernova is a stunning explosion, a sudden burst of light that can outshine an entire galaxy. But beneath that dazzling spectacle lies a deeper, quieter reality. Almost 99% of the energy of a supernova is carried away not by light, not by shockwaves, but by neutrinos. These ghost-like particles are the first to know when a star is dying, and the first to escape its collapsing heart. The story begins in the core of a massive star, where nuclear fusion has built heavier and heavier elements. Eventually, the star forms an iron core, a dead end for fusion. Iron cannot release energy through fusion, and gravity finally overwhelms the core. In a fraction of a second, the core collapses with unimaginable force. Temperatures rise to billions of degrees. Protons and electrons are crushed together to form neutrons, and in that process, a flood of neutrinos is created, an unfathomable torrent of particles that burst outward from the collapsing core. It is these neutrinos that play a decisive role in the star's death. As the core collapses, neutrinos rush outward, slipping easily through the dense stellar layers. Their departure removes energy from the core, allowing it to cool and stabilize into a neutron star. But at the same time, a small fraction of the neutrinos interact with the outer layers of the star, depositing just enough energy to reverse the collapse and drive the shockwave that becomes a supernova explosion. In other words, neutrinos help ignite the explosion itself. They are both the silencers of the core and the sparks that unmake the star's outer shell. The power of this process cannot be overstated. In the final seconds of collapse, the star emits more neutrinos than it has emitted photons in its entire lifetime. The density of neutrinos becomes so extreme that even these normally non-interacting particles briefly scatter and collide inside the collapsing core, one of the only times in the universe where neutrinos become a dominant physical force. Our understanding of this moment was transformed forever in 1987, When detectors on Earth recorded a burst of neutrinos from a supernova in the Large Magellanic Cloud, SN 1987A, only a handful of neutrinos were detected, but they arrived hours before the light of the explosion reached Earth. That early arrival revealed a key truth. Neutrinos escape instantly from the collapsing core, long before the shockwave breaks through the star's surface. SN 1987A was the first direct proof that neutrinos are not mere byproducts of stellar death. They are the primary carriers of its energy. Neutrinos determine what the collapsing core becomes. If the core's mass is low enough, neutrino cooling allows it to stabilize as a neutron star, a dense remnant only about 20 kilometers wide. But if the core is too heavy, even the neutrino outflow cannot halt the collapse. The core continues to shrink past the neutron degeneracy limit and becomes a black hole. In both cases, neutrinos are the first messengers, the first particles to escape, the first signals to reach us, and the first witnesses to the birth of a compact object. Neutrinos therefore connect the life and death of massive stars. They are the invisible signatures of core collapse, the heralds of supernova explosions, and the silent architects of neutron stars and black holes. Every supernova is a storm of light, but beneath that storm is a river of ghost particles carrying the true story of stellar destruction. While most neutrinos that pass through Earth are born in the Sun or our atmosphere, a far more mysterious population travels across unimaginable distances before reaching us. These are cosmic neutrinos, particles so energetic, so ancient, and so distant in origin that they serve as direct messengers from the most extreme objects in the universe. They come from the edge of cosmic violence, from the jets of supermassive black holes, from the collision of compact stars, from the afterglow of gamma-ray bursts, and perhaps from sources we have not yet even imagined. The IceCube Neutrino Observatory in Antarctica is the first instrument capable of detecting these titanic particles. While solar and atmospheric neutrinos carry modest energies, cosmic neutrinos can exceed anything produced by human technology. The highest energy neutrinos ever detected by IceCube arrive with energies millions to billions of times greater than those generated at the Large Hadron Collider. These particles are not created gently. They are forged in cosmic engines of astonishing power. Some of the most likely sources are blazars, galaxies whose central black holes fire jets directly toward Earth. These jets accelerate particles to near the speed of light, creating collisions that produce neutrinos of extraordinary energy. When IceCube detected a neutrino in 2017 and traced it back to a blazar 4 billion light-years away, it became one of the first moments in human history when we identified the birthplace of a single subatomic particle from across the universe. Other contributors include quasars, the blazing cores of young galaxies, where supermassive black holes devour gas and unleash energy on a galactic scale. Their turbulent accretion disks and relativistic jets are perfect laboratories for producing high-energy neutrinos. Even more dramatic are gamma-ray bursts, brief explosions that rival the brightness of all the stars in the universe combined. The internal chaos of these jets can hurl protons into collisions so violent that the resulting neutrinos become some of the most energetic particles ever observed. Why are cosmic neutrinos so scientifically valuable? Because unlike photons or charged particles, neutrinos travel through the universe unaltered. They ignore magnetic fields. They pierce through dust, gas, and galaxies. They do not scatter or lose their direction. When a cosmic neutrino arrives at Earth, it points almost perfectly back to its source. And because neutrinos interact so weakly, they carry pure information about the environments that created them, the temperatures, densities, energies, and processes occurring deep within cosmic accelerators. Every cosmic neutrino is a direct, unfiltered message from the heart of an extreme astrophysical event. A particle born in the maelstrom surrounding a black hole can travel billions of years through untouched cosmic darkness and strike a single molecule of Antarctic ice, producing a flash of blue light that tells its entire story. These neutrinos bridge the largest and smallest scales, from the heart of a collapsing star or a feeding black hole to a tiny burst of light in a detector beneath the Earth. They are the universe's most honest messengers, ghosts from distant corners of creation, arriving silently to tell us what no telescope can ever see. To understand how galaxies formed, how clusters emerged, and how the cosmic web took shape, we must look not only at matter and dark matter, but also at one of the most elusive ingredients in the universe, neutrinos. Though nearly massless and almost impossible to detect, neutrinos played a decisive role in sculpting the early cosmos. They drifted through the newborn universe like an invisible wind, influencing the growth of structure long before the first stars ignited. Just seconds after the Big Bang, neutrinos were already abundant. They decoupled from matter earlier than photons, slipping free from the dense plasma of the primordial universe and beginning their silent journey through space. These fossil particles form what physicists call the cosmic neutrino background, an ancient ocean of low-energy neutrinos that fills the universe even today. Though we have never detected this background directly, its presence is imprinted in the cosmic microwave background, CMB. Tiny fluctuations in the CMB's temperature reveal how neutrinos once flowed through space, smoothing out density variations and subtly altering the pattern of primordial ripples. These small ripples became the seeds of galaxies. And neutrinos, despite barely interacting with anything, influenced how quickly these seeds grew. Because neutrinos move extremely fast, close to the speed of light, they free stream through matter, ignoring gravitational wells and escaping regions where ordinary matter remained trapped. This free streaming acted as a kind of cosmic brake, preventing small structures from collapsing too early. In effect, neutrinos smoothed the fabric of the universe, suppressing the growth of tiny clumps while allowing larger structures to dominate. Their impact was profound. Had neutrinos been heavier or slower, galaxies would have formed differently. Had they been massless, structures might have grown too rapidly. Their exact mass shaped the very architecture of the cosmos we observe. Even today, neutrinos quietly influence the arrangement of galaxies. Large-scale surveys of the universe reveal subtle signs of their presence, slightly reduced clustering on small scales, and smoother distribution of matter in regions where neutrinos once passed unhindered. Cosmologists can even measure the total mass of all neutrinos in the universe not by capturing the particles themselves, but by studying how they changed the way galaxies aligned and evolved. Neutrinos are the invisible conductors of cosmic structure, shaping the rhythm of collapse, the scale of the cosmic web, and the delicate interplay between matter, radiation, and gravity. Though they rarely interact, their collective influence echoes across billions of light years. Every galaxy, every star, every cluster holds within it the silent signature of neutrinos, written into the history of the universe from its earliest seconds. In their ghostly motion, the cosmos found its form. For decades, physicists wondered whether the universe's most mysterious ingredient, dark matter, might simply be made of neutrinos. After all, neutrinos are abundant, they have mass, and they barely interact with normal matter. At first glance, they seem like ideal candidates for the invisible substance that shapes galaxies and binds cosmic structures together. But there is one crucial problem: neutrinos are too fast. Ordinary neutrinos move at nearly the speed of light, especially in the early universe when temperatures were incredibly high. This makes them a form of hot dark matter, particles that free stream across large distances before gravity can trap them. Instead of helping galaxies form, hot dark matter would smooth out density fluctuations and prevent small structures from growing. A universe dominated by fast neutrinos would look very different from the one we see today. Galaxies would form too late, too large, and too diffuse. The fine structure of the cosmic web simply cannot be produced by particles that move so quickly. For this reason, scientists now agree that ordinary neutrinos cannot make up most of the dark matter. Their mass is far too small, and their speed is far too high. However, the story doesn't end there. A compelling possibility is the existence of sterile neutrinos, hypothetical cousins of the known neutrinos. Unlike normal neutrinos, which interact through the weak nuclear force, sterile neutrinos would interact with matter only through gravity. They would be invisible even to the detectors designed to observe ordinary neutrinos. And unlike their fast-moving relatives, sterile neutrinos could be much heavier and colder, meaning they would behave more like the slow-moving particles needed to explain galaxy formation. This makes sterile neutrinos an attractive candidate for some fraction of dark matter. They could provide the missing mass without disrupting the cosmic structures we see. Their decay patterns might even leave faint X-ray signatures across the sky, signals that astronomers are actively searching for. Across the world, experiments are trying to uncover evidence of these ghostly particles. Projects like MiniBu-NE, Dune, MicroBu-NE, and Katrin look for subtle distortions in neutrino oscillations, hints that an unseen sterile state is mixing with the three known flavors. Space telescopes search for unexplained X-ray lines, and cosmologists analyze the large-scale structure of the universe for the telltale fingerprints of sterile neutrino behavior. The results so far are tantalizing but inconclusive. Some experiments show anomalies that hint at sterile neutrinos, others find no evidence at all. The question remains open, one of the most exciting mysteries in particle physics and cosmology. Could neutrinos explain dark matter? The answer is no, not the neutrinos we know. But their hidden siblings, if they exist, might be a bridge between the ghost world of particles and the invisible matter that shapes the universe. The next era of neutrino physics is about to begin. For decades, neutrinos have been the most mysterious particles in the Standard Model, light, silent, and almost untouchable. Yet they may hold the key to some of the deepest questions in cosmology and particle physics. To unlock these secrets, scientists are building the most ambitious neutrino experiments in history. One of the most important is DUNE, the Deep Underground Neutrino Experiment, currently under construction in the United States. It will fire a beam of neutrinos more than 1,300 kilometers underground, from Illinois to a massive detector buried deep beneath the rock of South Dakota. By comparing the neutrinos at the beginning and end of their journey, DUNE will measure how they oscillate, how they transform, and, most importantly, whether neutrinos and antineutrinos behave differently. If they do, this asymmetry could explain one of the biggest mysteries in cosmology: why the universe contains matter instead of annihilating into pure energy shortly after the Big Bang. In Japan, the next-generation detector Hyperkamiokande will dwarf its predecessor, providing an even more sensitive eye on the neutrino sky. With its enormous volume of ultra-pure water and its thousands of ultra-sensitive photomultiplier tubes, it will detect faint flashes of Cherenkov light from neutrinos coming not only from the Sun and the atmosphere, but also from supernovae in distant galaxies, and possibly even from relic neutrinos created during the birth of the universe. Both experiments aim to answer questions that linger at the edges of physics. What is the true mass of neutrinos? Do neutrinos violate symmetry between matter and antimatter? Did neutrinos help tip the scales so the universe wouldn't annihilate into nothing? Are there hidden neutrino species, like sterile neutrinos, waiting to be discovered? The answers may revolutionize our understanding of reality. Neutrinos, once considered footnotes in particle physics, may instead be the architects of cosmic history, the particles that decided whether galaxies, stars, and life itself could exist. Tomorrow's discoveries will not just reveal more about these ghost particles. They may reveal why we are here at all. In the end, neutrinos remind us that the universe is far richer than what our senses can perceive. At every moment, a dark river of ghost-like particles flows through your body, through the Earth, through every star and every atom. These particles come from the sun's burning heart, from the violent collapse of dying stars, from the jets of black holes, and from the first seconds after the Big Bang. They are the silent messengers of cosmic history, carrying with them the memory of events so distant and so powerful that no other signal could survive the journey. We never feel them, we never see them, and yet they pass through us in unbroken streams, stitching us into the fabric of the cosmos. Neutrinos turn empty space into a hidden ocean of motion, a universe within the universe, flowing in perfect stillness and complete invisibility. They remind us that reality is layered. Beneath light, beneath matter, beneath everything we think we know, there exists a world of particles that do not touch, do not slow, do not fade. A world that coexists with ours, indifferent and eternal. We live in an ocean of ghost particles, and each of them carries the light of places we will never see, and stories the universe entrusts only to them.